So it's Lue-Starkman, Professor Lue-Starkman, who has been at Case Western for 20 plus years now. 25 years, celebrating his golden, no, what is it, diamond, silver?
Silver.
Whatever it is. It's an important one. And he's really a foundational player in the world of CMB cosmology and studies of the early universe. And he has sort of an intellectual peripatetism, I guess, if that's a word, that really he's done everything from high-energy particle physics to topology of the universe, which we'll hear about today. Really fundamental issues that we take for granted. You know, is the universe a donut? You know, that would make Homer Simpson really happy, but it may or may not be the case topologically, not geometrically. We know a lot about the geometry, but what is it to say about the topology? We'll learn about that. And he's also really involved with sort of fundamental questions about whether the universe has anomalous spots and anomalous patterns. There's a great book by Jen Levin called How the Universe Got Its Spots. It's also related to topology, but in Glenn's case, he works on really anomalous anomalies, whether or not we understand why the universe has strange patterns in the temperature and now in the polarization of the cosmic microwave background. So he's here today. He was an undergrad at UT Toronto, right? He's actually a Canadian, and he's heading to the East Coast for a Simons workshop on fundamental physics. He was a PhD student of Dimopoulos at Stanford. And then he got to Case Western literally the year or so after I left, and so I missed out on his educational prowess. But I'll sit in your lap, don't worry. It's okay. We'll get cozy. But it's great to see this turnout, and before classes actually start. And I want to extend our gratitude for having Glenn come all the way out here to Southern California, basically to give this talk and hang out with our group. Thank you, Glenn.
Thank you very much, Brian. It's a pleasure to be here. It's been a long time since I was out in San Diego, and I always never forget how beautiful it is. But in fact, I wanted to say that the North Coast is also a very, very beautiful place. Cleveland is up here on Lake. A couple of places that people have asked me, "Where's Cleveland?" So it's up here on Lake Erie, and you have a lot of salt water, but a large fraction of the fresh water that's not frozen on Earth is in this set of lakes. And here's Cleveland on the pretty much the southernmost part of the Great Lakes. It has an important physics history because this is where the first really important experiment in American science, American physics at least, was done. The Michelson-Morley experiment, just outside my building. That's my building when it was built, back when the Rockefellers came from Cleveland and made all their money there. And this is what the area looks like now, with one of the best art museums in the country there, and arguably the best symphony orchestra in the country. And so this building sits right about here, and it looked just like this, except it's actually red. It's not black and white. For those of you who like newer music, this is the Rock and Roll Hall of Fame Museum, which is just down the street. And of course, the other place that got a really, really interesting building is our management school. So, all right. So what I want to talk about is the possibility that there are loops around the cosmos. And I meant to get out a piece of paper in advance because what I want to do is pick up on this point that Brian made, which is that we know a lot about the geometry of the universe, but not very much about the topology. So I think you'd all agree that if I took this piece of paper and drew a triangle on it, and I measured the angles of that triangle, that they would add up to 180 degrees to pi. And I think you'd agree that if I roll that up, and I went and measured those angles, since those are all local measurements, they'd be exactly the same, and they'd still add up to pi. And so it doesn't look like it, because in order to roll it up, I had to use the third dimension. But if I was living in this space, it's still a flat space. I haven't changed the local geometry anywhere, but I have changed the topology, because now there are shortcuts around the universe. And it's much harder to do in 3 dimensions, but I could take this and glue it onto that side, and then I would get what's called the 2 torus, and it would still be true there that the sum of the angles of the triangles would be 180 degrees. So we've learned a lot about whether we live in a space that looks like this, in which the sum of angles of triangles is 180 degrees, and the question is, what do we know about these other properties about the topology of the universe? So just to give you a sense, if we lived in such a universe in which, let's say, the fundamental domain was a cube, and imagine we live on the interior of a cube in which the left and right-hand side are identified like old video games, the back and front, and the top and bottom. We would sit here in the Earth, and we'd look out and we'd see another Earth, and there'd be other Earths all around us, and there'd just be this whole pattern of objects. As I said, the world may not be flat. In other words, the sum of the angles of a triangle may not be 180 degrees. It may be bigger, like if we lived on a positively curved space, or negative, like if we lived on a negatively curved space. And the same questions stand no matter what the geometry is. So for example, here is a fundamental domain in which you can make identifications, and this example works only in positively curved space. Okay, so in positively curved space, we can also have non-trivial topology. So that word spherical topology is kind of an odd thing, because I bet many of you have heard the expression that to a topologist, a donut is the same as a coffee cup. So how can I connect geometry and topology? Well, a fellow named Bill Thurston came out with a conjecture back in the 1980s, a very famous conjecture, which was proved by Perlman in 2003. And what it says is that every closed, so if I take a finite space that has 3 dimensions, and it's a manifold, which means it has certain smoothness properties, then I can always take that and divide it into pieces, each of which admits one of only 8 homogeneous 3 geometries. Okay? And those are flat 3-dimensional space, positively curved 3-dimensional space, negatively curved 3-dimensional space, positively curved 2-dimensional space, cross flat 1-dimensional space, and negatively curved 2-dimensional space, cross flat 1-dimensional space. And then these 3 other things that I have no idea what they are. Okay? But we don't worry about them usually in cosmology. In fact, usually we don't worry about we worry only about the first 3. We can try to worry about the next 2, but there really are very good limits on anisotropic curvature. Okay? But certainly these 3, actually, the last 3, if you look at them, the geometry doesn't seem to have anything to do with the universe we live in. Okay? So we can take space up, whatever it is, and carve it up into pieces at least, each of which have one of these geometries. I'm told, and I always worry now when I listen to topologists tell me things, because it turns out that they mean different things than we do. I'm told that generically you only end up with 1 piece. Okay? So most 3 manifolds have 1 piece, whatever most means. Okay? And those pieces are one of these 8, and we're going to focus on these 3, but certainly we could think about these other 2 as well.
How is S2 cross R, how is that homogeneous?
It's homogeneous, but it's not isotropic.
It's not isotropic.
Right. It's an anisotropic space. The curvature is flat in 1 dimension, and the other 2 it's positively curved. Right. And there's quite good limits about that. Basically, what would happen is that the first peak would move around depending where you were looking on the sky in the CMB. Mm-hmm. This is another tiling pattern, another fundamental domain that works only in hyperbolic space. All right, so we're used to looking for the curvature of the universe. How do we do that? We go out and measure the temperature, and I'm going to assume that everyone here knows about the cosmic microwave background. I'm not going to give you an introduction to the CMB, but I will remind you what we learned in cosmology kindergarten, which is that when you measure the temperature of the microwave background on the sky, what you're instructed to do is to then go and do a spherical harmonic expansion and figure out what the coefficients of the spherical harmonics are. And our standard model for the fluctuations around the mean temperature, notice I wrote delta T here, I mean T, that means I'm going to sum over only L's bigger than 0. So I'm taking out the average temperature. The standard model for those fluctuations is that the sky is what we call statistically isotropic. There's no special directions, statistically. and that these ALMs, these are realizations of independent Gaussian random variables. In other words, there's some abstract ensemble out there that these are drawn from, which is Gaussian. And if I look at ALM and some other L prime and M prime, and I ask, what do I expect from the product of ALM and Al prime M prime star? I expect 0, unless L equals L prime and M equals M prime. And then I get, my expectation is some number C sub L, which only depends on L and not M. And that part's the statistical isotropy. And if that's our theory, and our theory therefore tells us that what we really want to do, the only really interesting thing to do, at least to leading order, is to figure out what these C sub L's are in the underlying theory. Okay. And all of the interesting information is contained in these C sub L's, which are the average of the sum over M of ALM squared. Okay. Now, how do we go about and use that to measure the curvature of the universe? We notice that there is a fundamental scale embedded in the early universe, which is the fact that that sound is traveling through the early universe, and it can only travel a certain distance. So there's a sound horizon at the moment when the microwave background is released, and the photons can travel. And the size of that sound horizon, the angular size of that on the sky, is different depending on whether the triangle that it forms. Here we are looking out at it, we see some acoustic wave, and the angle of that triangle will be different depending on whether the sums of angles of triangles is 180 degrees or more than 180 degrees or less. And that will mean that this peak in the angular power spectrum, what I'm plotting here are these C sub L's that I told you, all of the interesting information in these C sub L's. So here's the pattern that the theory tells us it should have, okay? And where exactly these peaks are depend on the curvature. Okay? And it'll be someplace if the universe has flat geometry, it'll be somewhere else if it is positively curved geometry, somewhere else if it is negatively curved isotropic geometry, and if it had anisotropic geometry, it would be in different places in different parts of the sky. And somewhere around about 2000, people were able to measure that and found an answer consistent with it being flat. Okay. Now, things are a little bit more complicated maybe today, almost 20 years later, where they're consistent with it being flat, but depending on how you look at it, maybe there's some evidence, some weak evidence that we actually live in a positively curved universe. Right? If you just look at the evidence from the CMB, you find that the omega in curvature, okay, thinking of it as an energy density, it isn't, but that there's some evidence for for positive curvature, okay. But if you add in other contributions to other types of data, that evidence goes away, okay? And probably this is all connected to the tension over the Hubble constant as well. Okay, so these are at the level of, it used to be that in cosmology we would argue over factors of 2, then over 10%, and now we're arguing over a couple of percent.
I think Planck claims that it's the over-smearing of the high L peaks, the same as so this is just a different version of the lens.
Yes, right. It's just a different version of
Well, whether that's related to H0 is
true.
But that one,
Yes,
that shows up in many different places.
Right. So, what about topology? So there's this long history of looking for the curvature of the universe. What about looking for the topology? Well, that goes back even before general relativity. Schwarzschild thought about it. De Sitter thought about a topologically non-trivial version of Einstein's positively curved his S3 universe almost immediately after Einstein came out with his original cosmology, and kind of episodic, irregularly ever since then, people have thought a little bit about topology. So how do you go about looking for topology? And the first thing you'd think of is, remember I showed you that beautiful picture of the Earth. If I'm sitting here, there's another copy of the Earth over there, and another one behind it, and some more. So why not go look for objects that are repeated? So for example, I see Einstein here, and I go look out somewhere over there, and I should see another copy of Einstein. Well, the problem is, if you think about it, depending on where you're looking, you're going to see those objects at different distances, and then therefore at different times in the past. And so you may look close by, and you see Einstein as you know, at one age, and you look further another direction, you see him at an earlier age, and you have to recognize that those are in fact the exact same person. Right? So I may look out and see some galaxy or some quasar over there, and now I want to look for it, but I have to do that, I have to figure out what it would have looked like at a different age. And that's not so easy. You also may not see it in the same orientation. In fact, typically you won't see it in the same orientation. Even worse, good chance if you're looking at it from the front, you're going to see it from the back. So things may look completely different. Okay? And in fact, it may have even evolved into a different object. Right? You may have had galaxy mergers in the meantime. So the object that you're looking for may not be the same object as it was, but the evolution or predecessor of the object that you're looking for. Okay? So people have tried to use object searches to look for topology, but it's really tough because of this problem. You have to convince yourself that you really would recognize the objects in the different directions. And so probably the most promising place to look for topology is in the cosmic microwave background. Why is that? Well, probably the most important thing is the CMB is all at the same distance. Right? No matter which direction you look, the surface of last scattering is, to a very good approximation, at the same distance. And so this idea, this worrying about how things evolved, that piece of it at least we take out. Now, it's not the case that we're going to take out the fact that we're looking at things from different sides, so we're going to have to figure out how that imprints. Okay? So there's three basic ways that we can imagine looking for topology in the microwave background. The first is to remember and they actually all come from, remembering where does the microwave background come from? What is producing these fluctuations in the early universe? Okay. Well, those are all the imprints of sound waves that have been traveling through the universe, acoustic waves that have been traveling through the universe for 400,000 years. We believe that the origin of those sound waves is that there were a scalar field, we call it the inflaton, and that had fluctuations that were generated quantum mechanically. And so we are looking at excitations of the eigenmodes of that scalar field, okay? The imprints of that. Okay? And if we change our space, change the boundary conditions of our space, impose periodic boundary conditions, topological boundary conditions, we're going to change the spectrum of modes. We're going to change the eigenmodes entirely. They're no longer going to be Fourier modes, they're going to be superpositions of Fourier modes, or the generalizations of those to curved space. So for one thing, the spectrum of modes will become discrete. There'll be a long wavelength cutoff. There'll be a wavelength beyond which you can't get any modes if the universe is compact in all directions. So there's this idea that the spectrum is the topology. So if we could measure the spectrum, we would learn the topology. In fact, there's a very famous question by an algebraist named Mark Katz. Can you hear the shape of a drum? And the answer is no, if you're a mathematician. And what do I mean? Well, it's no in precisely the sense that a mathematician would mean is that there are counterexamples. There are what are called isospectral drums. So here are the shapes of two drums that are different, that have exactly the same spectrum of eigenmodes. And here are two drums that are even more special, which is that these two shaped drums, which are different, if I strike this one here and this one here, I will get exactly the same sound. Okay? They're called homophonic drums, but they're rare. Okay? So generically, if you take two different shaped drums, you can hear the difference between them. And so if you think about it, what we're really asking is, can we hear the shape of the universe? Because we have acoustic waves in the universe. We're trying to extract the spectrum of the eigenmodes, right, the spectrum of the scalar wave operator, by looking at the acoustic waves, in other words, by listening to the drum.
This is sort of geometrical, not topological.
Well,
two shapes
in this
different-
case, I imposed zero boundary conditions at the edge, and a question that hasn't been. There are all sorts of mathematical questions that are generalizations of this which haven't been answered. Like, what happens if it's not zero boundary conditions, but topological boundary conditions? What happens if you don't have perfect ears? Right? How much information do you lose if you cut out some of the low frequencies? Is the information sitting in the low eigen frequencies, or is it sitting in the infinite number of high frequencies? People don't know the answers to those questions.
How does this depend on the dimension? So this, you gave the 2 dimensions.
It's also not known how this depends on the dimension. Right? So there's a whole. I talked a little bit to Peter Sarnak at one point, who studies these kind of things. Apparently, there's all sorts of open questions in this area that aren't known. So in principle, one could try a very generic search to measure the eigenmodes and the eigenfrequencies and figure out what the eigenspectrum is of the scalar wave operator, and that would tell us what the topology is. That's very challenging because we only have one universe. We only get to measure it once. At the moment, we only really get to measure it on the surface of last scattering. If we could do a tomographic survey, if we could look at many concentric spheres out to the last scattering surface, it would probably be better. But ultimately, maybe this is the way we'll nail it down. Another way to go is to compute the correlation function. Now, we do this normally. We take pairs of points on the sky, and we take the products of their temperature, and we average over those. Okay? And that will be different in each space. Okay? That will be different in every different manifold. It can be worse than that. It can be different in different places in every manifold. Okay? So because these spaces break homogeneity. Okay? But this is one of the leading ways of trying to look for topology, is to compute the pixel-pixel correlation function, the product of the temperatures in different places on the sky, and compare it to what we see to what's expected. Actually, you do this in modal space, not in pixel space. So this is one of the methods. And then what we've focused on over the last 20 years as a way to do it. See, the challenge with this method is that, as I said, what you expect from the pixel-pixel correlation function is different in every single space. Okay? And there's an infinite number of different spaces to look at, which is challenging computationally. Okay? It's worse. Each of those spaces, many of those spaces have up to 6 real parameters to describe exactly how they're configured. So, for example, I showed you a cube. But instead of showing you a cube as the fundamental domain, I could have stretched one of the sides, I could have stretched one length of the cube, made it longer in one direction than the other two. Okay. I could also tilt the cube, right, and get parallelepipeds instead of rectangles for the faces. So there's an awful lot of possibilities, and you worry that when you discover one that fits the data better than the simple topology, that all you've done is paid a huge look elsewhere penalty that's hard to overcome. So what we did is we took a different approach called circles in the sky, which is one that doesn't care about what space you live in. And so think of yourself to understand what that is. Let's go back to this 3 torus picture where we live in a space that is a tiling of the infinite Euclidean 3 space. Okay? And so let's take 2 neighboring Earths and imagine that we are on Earth doing a microwave background experiment. And that means that we are looking at light that is coming from the last scattering surface, and that last scattering surface is centered on us. Of course, there's nothing special about our location. Anyone, anywhere, if they did a microwave background experiment, would be getting photons from their last scattering surface, which would be a sphere centered on them. So here we are going down to, let's say, can I find Chile on here? No, I can't because it's turned the wrong way. Okay, so we're going to go down to the South Pole, and we're going to do a microwave background experiment, right? And we're going to have a last scattering surface. And so is this copy of us over here going to do a last scattering, going to do a CMB experiment, and they're going to have a last scattering surface. And if our nearest copy is close enough, then those last scattering surfaces are going to intersect. In other words, here's my last scattering surface. I look out. Here's me over here. I look at my last scattering surface. And if those last scattering surfaces are close enough, then there's a circle of points at which this copy of me sees over in that direction, and this copy of me sees over in that direction. And so we can compare the pattern of temperature fluctuations on those two circles should be correlated. They would be exactly the same, except for there's all sorts of effects that make them different, like the fact that the light has to travel from the last scattering surface to us. And that changes, that also induces fluctuations. The fact that the material on this surface is moving, and so there's a Doppler effect, which will give different contributions to this circle and this circle. But the dominant contributions to the fluctuation of the temperature fluctuations on this circle are what's called the Sachs-Wolf effect, which is that you have to climb out of the gravitational potential, or that is on that surface in order to get to us. Okay? And that gravitational potential will be the same around this circle and this circle, so there'll be a pattern of fluctuations that I can look at and compare.
But if my copy is at a distance of 20 billion light years, then I don't see it.
Right, so if my copy is too far away, the last scattering surfaces don't intersect, I won't find any circles. Right? So what I have to do is I have to go out and look at all circles of the same size and compare the patterns around them. Okay? And we'll talk about that in a minute. And it was shown by Jeff Weeks, who's a student of Bill Thurston's, very accomplished topologist in his own right, that if you find the pattern of circle pairs, it's unique. There's a unique correspondence between those and the manifold. Okay, so you actually know what space you live in. Yeah.
So
Dan.
for some of those effects you mentioned, you wouldn't worry about the polarization.
Correct.
But now I guess you're worrying about the angle. You have to line up the angles.
Right.
What's worse? Is that what you gain?
Well, so it'll turn out. Ask me that question later. Remember that question and ask me later. So I've told you that we might be able to look for topology, but the question is, why bother? Well, one reason is because we can. It would be really interesting to discover the topology of the universe. But I want to suggest some further reasons. So let's come back to this idea that we calculate the angular power spectrum. So here is from 2013 what the angular power spectrum would have looked like. You know, it's kind of this amazing, complicated set of points that are fit by this 6-parameter, and I would argue actually 7-parameter fit, that there's no such thing as a 6-parameter fit in this case, but to way more than 6 points, right? And so this is pretty remarkable. And of course, it's not just that power spectrum, which was the temperature power spectrum. There are also cross power spectrum. There's also the polarization power spectrum, and I think I put here the cross power spectrum between temperature and polarization. You know, so way more than 6 points being fit, or 7 points being fit by just 7 parameters. And it's this that more than anything, drove us to where we now have many zeros in our plus and minuses in a field that before this would have been worried about 20% effects or 50% effects or a factor of 5 effects. So astonishing experimental accomplishment and a remarkable agreement with theory, especially for statistics like the one we've just looked at, that the theory prefers. But there's a big but. And that but, one of those buts at least, comes when looking at the large angles or the low L's. And so I want to tell you about several of the ways in which the lowest L's, the largest angle properties of the cosmic microwave background, aren't fitting into this story quite as beautifully as you would like. And I want to start doing that by looking at CLs, at this angular power spectrum, and pointing out things that are anomalous. So I want to start by pointing out something that everyone said was anomalous and really isn't. Right? But it is how I think people initially got started. So that my animation died. That says the low quadrupole. So there's this. The C2 seems to be quite low. So if you're not used to seeing CMB plots, this is the measured angular power spectrum, those C sub L's. This line is the best fit from the theory, this curve, and you can see this gray band around that, and that's the uncertainty induced by cosmology, by the fact that we only get to measure 2L plus 1 ALMs of each L. Okay? So up here at L equals 200, that means we get 400 estimators of the value of C200, but down here at L equals 2, we get 5 chances to measure C2, and so we don't expect to do a very good job. We would like to measure this number with it, but we'll have an error bar this big, but nevertheless, this number is small. The quadrupole is small. The thing is,
sigma is that 1.5?
Yeah, exactly, and that's exactly, and that's
Who cares?
exactly, yeah, no, who cares, right? But it was the first thing one of the first things people said. Oh, that's kind of odd. Why is it so small? Okay. There is something. There is another thing in the CLs down at those low L's, which is kind of odd. If you notice. So here's L equals 2, and then L equals 3 is above it, L equals 4, and then L equals 5 is above it, L equals 6, and L equals 7 is above it, 8, 9 is above it, 10, 11 is above it, 12, 13 is above it, 14, 15 is above it, 16, 17 is above it, 18, 19 is above it. Okay? So for some reason, it always goes up. Right? The odd ones are stronger than the even ones. And according to the theory, there is no correlation among these L's. Okay, here is more of that angular power spectrum. We focused on this L equals 2 before, but there's actually others that are even more anomalous. Okay, there's this dip in the first peak, this other dip at L of about 20, this glitch at L of 40. So, we could sit here and figure out how often this should happen. But here's something really strange that was in the very first WMAP first year paper, the very first version of their paper about the angular power spectrum, but that disappeared from all future versions. This figure, in which this curve has been separately calculated over the part of the sky near the ecliptic plane, the plane of the solar system, and in the part of the sky perpendicular to the plane, so the ecliptic poles. And what you'll notice is that dip at 20, that glitch at 40, and that dip and the first peak are all in the ecliptic polar regions. And in fact, what we've shown is that this one turns out to be exclusively near the ecliptic North Pole. So these are, how significant are these? I'm not going to go into the details of that. All of this is what's called a posteriori statistics, which means I go look at these things after I already have the data. I didn't tell you I was going to look at them. Should I have looked at them? Should I have not have looked at them? What penalty should I pay for doing that? It's not clear. Okay. So let me tell you some other. That is if we look at these C sub L's. Remember, the theory told me the only thing that's interesting is calculating the angular power spectrum and measuring it, because the universe is statistically isotropic. It doesn't matter what individual ALMs are. It only matters what the average of their square is. So I want to ignore that and ask, And this came out of trying to think of ways of looking for topology, but I want to ask a different question, which is, what are the directions associated with the Lth multiple? In other words, if instead of summing over L and M in this spherical harmonic, what if I just sum over M? Okay. And that makes sense because the universe is supposed to be statistically isotropic, and so each L kind of is independent. These are the things, these ALMs are the ones that contribute to a particular C sub L. And for L equals 1, in fact, we rarely think of A1M, A10, and A1 minus when we think of what's called the dipole, which is some vector which has some magnitude and direction. Okay? So instead of writing A1M, 0, and minus 1, we write some strength of the dipole and some direction of the dipole dotted into the unit vector. And that's a better way of thinking of the dipole in some ways because this U hat is a vector. It's really a pseudo-vector, but it's okay. And A is a scalar under rotations. And so C1 and A1 only depends, only A1 depends on C1. So measuring A1 is the same as measuring C1. Okay. Now, you can do the same things at higher L. You can think of L equals 2 as the product of 2 dipoles. L equals 3 is the product of 3 dipoles, etc. You should be careful and subtract out all the traces. But you can replace the 2L plus the 2L plus 1 ALMs by L unit vectors and a scalar. And the point is that those L unit vectors are vectors, that A is a scalar, and the only thing that's supposed to be interesting is that scalar. The directions of all these dipoles, what are called multipole vectors, are supposed to be completely uninteresting, according to our theory. We were very excited when we invented this way of representing data on the sphere, until someone pointed out that it had been done before. You may have heard of him. His name is Maxwell, and he wrote this not very important book. Okay, and this is how he thought of data on the sphere as products of L directional derivatives of the 1 over r potential on the unit sphere. Okay, so it's just another way of representing, instead of spherical harmonics, it's another way of representing data on the sphere. So the quadrupole can be represented by 2 vectors. In other words, you can think of it, the quadrupole as a plane, and the octupole by 3 vectors. In other words, you can think of it as a solid or as 3 planes. And so you can think of what we call the area vectors, which just are the areas of those planes, so the normals to those planes. And those are an interesting way to think of it. So what I want to show you is the area vectors of the quadrupole and octupole. And I'm going to do it in this really weird projection because that's how we always did it, and that way no one can claim that I'm trying to change things up to make it look better. Okay, so here is the area vectors. So remember, the quadrupole is a plane, the octupole is 3 planes, and the quadrupole and octupole, according to our theory, are completely independent. Right? So these should point in random directions. Okay. All right, so here, and I plotted in both the northern and southern hemisphere. In other words, I don't know whether to point my normal vector this way or this way. So here is the normal vector to the quadrupole in darkish gray, and here are the 3 vectors of the octupole in dark black. So up here, it's hard to see them because this really is somewhere over here. So here they are. Let's look in the southern hemisphere. Here are the 3 octupole vectors. Here's the quadrupole vector. So they should have been distributed everywhere in this southern hemisphere, but they're all clustered around here. And that really is a pretty small region for them to be clustered in. You'll notice that there's another dot there. That's actually the dipole, the direction of the Earth's motion through the microwave background. There's this dashed line here, and I'm going to stick in all the things that we could imagine would be affecting the experiment. Okay, so all the astronomical directions or planes that might have been contaminating the experiment and causing systematics. So there's the ecliptic, which is the plane of the orbit that the experiment was in, whether it's WMAP or Planck. The dipole, which is the direction of the Earth's motion through the CMB, approximately. The equinox, I have no idea why we put that on there. The supergalactic plane, I'm not sure why that should matter, but someone told us to put it on there. Okay. And so what do you see? You see that these are all clustered together, and maybe that they're near the dipole, and the dipole happens to be near the ecliptic, so maybe they're also near the ecliptic plane. Okay. So what we can say is that these four planes, the plane of the quadrupole, the plane of the octopole, 3 planes of the octopole, are for some reason aligned with one another. There's for some reason essentially perpendicular to the ecliptic, and they're for some reason normal to the dipole. Okay? I don't know if any of these are, which of these are important. It's hard to imagine that anything but systematics would be responsible for these last two. Okay? So if these are important, then that says that this is all systematics. On the other hand, that would be really strange. It would say that the quadrupole and octopole we were measuring in the CMB, which are supposed to be there, are actually caused by systematics in the experiments. And that the different experiments have the same systematics. How good are these alignments? Well, the quadrupole and octopole planes are aligned with each other depending on the map that you use, somewhere between 1 in 1,000 times and and 1 in 150 times. Okay? Having those, once those quadrupole and octopole planes are, these 4 planes are aligned with each other, asking how often are they this perpendicular to the ecliptic? Oh, somewhere between 0.2 and 2% of the time. Once the quadrupole and octopole planes are aligned with each other, and this perpendicular to the ecliptic, how often are they as aligned as they are to the dipole? Oh, a few % of the time. So, and let me leave out the last one because it's less interesting. I don't know if I can multiply these together. I don't know which of these to believe, but what we do see is that the lowest L's are not behaving as though they are statistically isotropic. Okay. And here's a nice picture of them. Okay, so what I've done is this is actually just the quadrupole, and I'm showing you what different maps, what different Planck and W maps have for these area vectors for the quadrupole. And you notice that they're always tightly clustered, right? Which just says that no matter whether you measure this with W map or you measure with Planck, no matter what method you use to clean your map, to take out the foregrounds, no matter what method you use to infill the galaxy, you get the same answer. It does not seem to be, so if it's systematics, it's some deep systematics. Okay? And the same thing's true of the octopole. None of this matters. It's also interesting, and I don't show this here, that when we realized that we needed to so that we believe that the dipole of the CMB is due to our motion through the universe. Okay, and everyone knows to subtract, therefore not to look at the dipole. It's not interesting. It's not cosmology. It's just the Earth's motion through the universe, probably. Okay? But people hadn't been worried about the fact that that would actually contribute to the quadrupole. And when we subtracted the Doppler contribution to the quadrupole, that pulled the quadrupole and octopole vectors together much more tightly. Okay. So what are the conclusions about that? Well, these alignments are persistent. They're individually interesting, collectively significant. We have no good explanation for them. There's something else really strange about that low L stuff, not just the quadrupole and octopole. So as you pointed out, who cares about a low quadrupole? But that isn't actually what's strange about these low L's. It really should be called the large angle anomaly. And here's why. So before COBE, which was the original all-sky measurement of the microwave background back in the 1990s, the Cosmic Background Explorer, astronomers weren't interested in angular power spectra. They were interested in angular correlation functions. Okay? And so when COBE was proposed, they thought they were going to go out and measure the angular correlation function, which is take the temperature in any two directions that are separated by some angle theta and multiply them and average over all pairs of directions like that on the sky, and that's the angular correlation function. And the thing is that you can exchange the information in the angular correlation function for the information in the angular power spectrum, and our theory tells us that it's much better to calculate the angular power spectrum because the C sub L's are statistically independent. And clearly, if that's true, the angular correlation function at different thetas isn't. So the statistics of it is much more complicated. Okay? But eventually, but by the time COBE reported its results, people had realized the theory was much more interested in the angular power spectrum, and so they mostly didn't tell us what the angular correlation function is. They finally got around to it in one of their last papers, so here's what it looks like. What you should notice is that above about 60 degrees here, it seems to be very close to zero. But very little, this was noticed. I'm not showing you here what's expected, I'll do that in a second. But it was noticed, but no one really focused on that. So here, from the next good measurement of that by WMAP, is what the expectation is. That's this dashed line, with these kind of error bars around them, and you shouldn't think of them as normal error bars because they're highly correlated with one another. So this is what the theory tells us, is that the data should lie kind of in this band. Okay? And here's what the data looks like if you take it from any of the individual bands that WMAP measured. Okay, so they all sit like this. And notice that just like COBE, they sit here at 0 from about 60 degrees to 170 degrees. Now, if you go ahead and look at what's reported eventually for the angular correlation function, you see instead this curve, which isn't at 0. Okay, that's this ILC full, okay, or the maximum likelihood estimate, something built out of the maximum likelihood estimate, that seems to not be 0. Okay, those are processed pieces. That's processed information about the two-point correlation function. If you take the sky map outside of the galaxy and calculate the two-point correlation function, you'll get this dash curve which agrees with all of the individual bands. Okay? And then they have to go ahead and they have to figure out, well, what is even though we don't trust the data in the galaxy, what do we think the data in the galaxy is essentially? It's much more rigorous than that. But when you put in what you think the full sky is, and then calculate the two-point correlation function, you get something that has correlations between 60 degrees and 170 degrees. So you measure no correlations, but then you infer correlations. It's very strange.
So that means if I look there and measure the temperature there, then it's probably, if it is a bit hotter, that's a bit colder.
No, it's not anti-correlated, it's uncorrelated. I have, from measuring it there, I get no information about there. Yeah, once those are more than 60 degrees apart.
How is that reflected in the power spectrum?
Great question. I'll tell you in a minute. Okay. So this, one measure of that is this property S1/2, which is the integral from 60 degrees to 180 degrees of C of theta squared. So it's not that this curve, whichever these curves, lies so far outside of these broad error bars, it's that it's 0. It's very strange. Okay? The theory told us this wasn't an interesting question to ask. But when you ask it, you find that the answer doesn't agree with the theory. Okay? So this has persisted in all of the cut sky maps with p-values of 0.04%. So that's 4 times 10 to the minus 4. 0.04%, 0.02%, 0.02%. The full sky maps will have 5%, but the cut sky maps, the parts that exclude the galaxy, it'll be like 0.02, 0.04%. And it'll turn out that all of the correlations pretty much from 60 to 175 degrees come from pairs of points, at least one of which is inside the galaxy. So if you have both points outside the galaxy, no correlations. But if you start putting points inside the galaxy, then you start to see correlations. Did this change in Planck? No. So this is a property of the sky that we see, apparently, not a property of the experiment that we're doing. So, somewhere between 0.03 and 0.1% of realizations of the model of inflation have so little cut-sky large-angle correlations. Now, if you ask the question, what does this mean for the angular power spectrum? How would you get no two-point correlations? Well, remember that C of theta is the sum over L of C sub L PL of cos theta. And so one way to get C of theta to be 0 is to set C sub L equal to 0. Well, except that's not what we see. So what's happening instead, actually, is that those low LCLs are canceling among each other in this series. And that's really hard to see if you look at the angular power spectrum, but when you do the Legendre transform, and to C of theta, you see that there is something strange, that the C sub L's are correlated with one another in a way that's completely unexpected in lambda CDM. In fact, it's really, really a very big puzzle in lambda CDM, because even if we replaced all of our theoretical C sub L's by their measured values, so let's just say, okay, I don't know how, but I'm going to change the theory to equal the measurements and take that as my new theory. Okay? And now I go ahead and I take the ALMs, which are Gaussian random variables, but now with those C sub L's, you'd think I would get back no two-point correlation function, but I don't. And I don't because of cosmic variance. I don't because when I pick those Gaussian random variables, I don't recover the theoretical C sub L's. I recover the theoretical C sub L's plus those big wide error bars, and that means that they don't cancel with each other in the way that they're supposed to. And so if I do that, there's only about a 3% chance that I will get as little correlation as I do in the sky that I see. And when you go and look at those, almost always it's because they all the C sub L's happen to come out low. Okay? So you almost never get what we see on the sky. So how did this happen? It could be a fluke. That's the simplest explanation. We just happen to live in an odd realization of lambda CDM. Or it could be physics. Well, if it's physics, what would that mean? It would mean that one thing it could mean is that if we want to keep this idea that the underlying processes are Gaussian, it would mean that the basis we're using is the wrong basis to be Gaussian. So, I don't know of any other explanation other than that. So how could that come about? One way is that the universe has non-trivial topology, because that means that the modes I used were the wrong modes. Another way is that maybe, and this seemed to me completely reasonable, maybe I don't actually have long-distance correlations. Because think of a Fourier mode. A Fourier mode is really strange. It has infinite distance correlations. If I give you a Fourier mode and I tell you its value here, and I tell you what k it has, I can tell you its value anywhere. So it has infinite length correlations. That seems weird. Maybe the real things are more like wavelets. They look like Fourier modes, but after some point they kind of decay away. And well, we thought that was a really good explanation. It just turns out not to work for interesting reasons. Let me tell you about one more thing that's really odd about the large angle universe. And then I'll come back and finish with how this is related to topology. So here is the sky. Actually, I think this is probably a later sky than that. But this is one thing you might notice about this sky if you look at it. It's a lot kind of busier here. It's a lot more. There's more power down here than up here. And that was first noticed by Bennett et al. In 2003, and there's papers by Erickson 2004. Many, many people have noticed this. It's usually described as the dipole asymmetry. You know, there's this dipole in power. You know, strong power here, weak power here. And I actually think that's the wrong way to describe it. It turns out that if we use the high L's that you can't really see here to predict what the low L sky should be, what this sky should look like, down here it's just right. It's doing exactly what it's supposed to be. And up here, it's not. So if I look at, characterize this, I can characterize this by the variance, okay, in the north and the south. In the south, so here is the probability distribution function for the variance on half the sky. Okay? And the south sits, you know, right near the mode of the distribution, right near the median of the distribution. It's completely ordinary. And the north sits down here, you know, with only 0.1% of realizations below it.
What is on the vertical axis?
This is the variance in some units. It's not in arbitrary units of the temperature. Okay, so this is the temperature variance on the southern sky and the northern sky. South is normal. The north is really strange. Okay. So how strange? Well, about 1 in 1,000 skies have this little variance in one of their hemispheres. So with so many anomalies, what do? Okay. We go measure things about the northern sky.
Sorry, Glenn,
Yeah.
if you change the orientation of the hemisphere, how you cut the hemisphere, what happens? Have you chosen a cut here that accentuates the difference?
So the ecliptic is not the perfect cut. You can make the cut a little bit better. Yeah. So you can ask what there's always in all of these things there's a posteriori statistics, and that's why. What's really interesting is how do you go check that these are real as opposed to flukes, and that's another talk. Yeah.
You quoted about 0.1%. Is that doing a simulation and picking the best possible cut and asking how big the variance is? That's doing a simulation or taking
That was not marginalizing over hemispheres. That was asking north versus south.
Okay.
Yeah. That was asking how often is a hemisphere that low. So it's
the hemisphere is defined the same way.
Yeah. Take a hemisphere, ask how often is it that low. Okay, so what does this have to do with topology, which is supposed to be the topic of this talk? So here is a paper from 2009 by Bielovich and Riazuelo. And what they said is, suppose the universe has one small dimension, right? It's compact in one of the dimensions. And they looked using multipole vectors at the quadrupole and octopole. So this is what that universe would look like. It had two dimensions that are large compared to the last scattering surface, and in one dimension it was small. And what they found was that typically they would have quadrupoles and octopoles that were planar and aligned in the way that we see. Okay? Now, it was statistically favored, but it wasn't enough to rule out, you know, the universal covering space, rule out that there was no topology, but it was favored. So last year we looked at very similar things that are called slab topologies, and we showed that if our universe is flat and has one compact dimension of appropriate size, this would suppress the large angle, the angular correlation function from 60 degrees up. If you chose it to be the right size, as you adjusted the size, you would change the range of angles over which you suppressed it, while maintaining a low angular power spectrum consistent with observations. It said that, in other words, it wouldn't set the CLs to 0. It would arrange for this conspiracy. Now, the only problem with this was that both of these conflict with existing limits. So remember, I told you about the circles and how we could search for the topology with the circles, and we've done that. We did that. We did that first in the early 2000s, and then we went and did it better. So here is us looking for, with some statistic S, for circles in some universe that someone gave us, that Riazuelo gave us. He didn't tell us what it was. He just said, here is a sky. Does it have circles? And we said, well, it has circles that have angular radii of 70 degrees, 63 degrees, 61 degrees, etc. We found all these places where it has circles. And he said, well, you did pretty well. Your false negative rate was, less than 0.02% for all circles that were bigger than 42 degrees, and 2% once they were 24 degrees. So we're pretty good at finding circles, and when we looked in WMAP, we didn't find any. And then when the Planck team looked, they used the circle search. They used something. But they didn't do the proper circle search. They only looked at circles that were back to back, where you really have to look at pairs of circles that are in arbitrary directions on the skies. So we did. We don't find circles. We don't find circles all the way down to. All the way down actually from 10 degrees all the way up to. I'm not sure we. Up to 80 degrees, and all center separations from back to back all the way down to 11 degrees. Yeah. And so that tells us that the shortest path around the universe is greater than 98.5% of the last scattering surface, which rules out those slab topologies with the size that seem to explain things.
What was the size of that?
The size was 0.7 times the diameter of the last scattering surface, approximately.
0.7.
0.7, and we ruled out up to 0.98. So where does that leave us? The large angle CMB is extremely anomalous. Cosmic topology may be Y, but it's not a simple slab topology. There's work to be done in looking at other topologies, because it turns out that there's all sorts of things very like the slab topology that aren't ruled out by the circle searches or by the mode searches. And there's measurements to be made to see if some of these anomalies are statistical flukes or if they have physics behind them. Thanks.